Okay, let's unpack this. Every day, you hear a static number quoted, a poll result, an average salary, a satisfaction rate.
Right, a single number, the point estimate.
Exactly. And that figure, it seems so solid, but it's always hiding a degree of uncertainty. If you really want to be well-informed, you have to find a way to quantify that hidden doubt. So today, we are diving deep into statistical inference and this idea of interval estimation. It's really the art of using a range to represent your findings. Specifically, we're talking about confidence intervals.
TIs, yeah.
The sources gave this fantastic hook to understand this. They said if a point estimate is like fishing in a murky lake with a spear,
I love this analogy.
then using a confidence interval is like casting a massive net. So our mission today is to figure out exactly how to cast that net. How wide does it need to be? That's the margin of error.
The MOE.
And what even gives us the right to cast it in the first place? That's the central limit theorem.
Absolutely. And what's so fascinating here is that interval estimation, it's one of the foundational pillars of statistics. It's the tool that lets us take a manageable small sample and then make valid, reliable generalizations about a whole population that would be impossible to measure completely.
So you're defining the bounds of what's reasonable.
Exactly. And to do that, we need two key concepts right up front. First, the confidence level, usually 95%. That's the middle of our net.
The area we're trying to capture.
Right. And then second, there's the significance level, or alpha. That's the leftover bit, the 5% in the tails. It's the risk that our net misses the fish entirely.
Okay. So let's start with the really basic problem then. Why do we need a net at all? I mean, we rely on these sample statistics as proxies, but we know they're not perfect. They vary.
I always vary.
Think about this example. If you randomly sample 1,000 adults and measure their average height in, say, Texas, and then you do the same thing in California,
you're not going to get the same number.
Not the exact same number.
Yeah.
But, and this is the key, they'll only be somewhat different, right? They'll cluster around the true national average.
That clustering is the entire game. And quantifying just how much they cluster, how much they vary, that's what lets us define the margin of error. And this is where the central limit theorem comes in, the CLT.
The bedrock of all of this.
It is the bedrock. It says that as your sample size gets large enough, it doesn't matter how weird the original population data looks, the distribution of your sample means will start to look like a normal distribution.
That perfect bell curve.
That beautiful, predictable bell curve.
Yeah.
And that symmetry is what gives us the power to calculate our confidence interval.
So because the CLT gives us that symmetry, we can just calculate the range. The formula looks pretty simple. Point estimate plus or minus the margin of error.
That's the one.
But all the magic or the trouble is in the margin of error, isn't it? What actually dictates the width of that net?
It's dictated by two things. First, how confident you want to be. That gives you the multiplier. And second, the natural volatility of the data, which we call the standard error.
Standard error. So that's just a measure of how much the sample statistic bounces around naturally.
Precisely. It's the standard deviation of that sampling distribution. The more your data bounces around, the wider your net has to be.
That makes perfect sense. Okay, let's make this concrete. Let's talk about estimating the population mean mu.
Okay.
Now, the calculation method changes based on one critical piece of info. Do we know the true population standard deviation, sigma?
Right. And the ideal textbook scenario is that you do know it. If sigma is known, maybe from historical data, we get to use the standard Z distribution.
And that's where we get that magic number, 1.96. When people say 95% confidence, that's the Z multiplier they're using.
1.96 standard deviations out from the mean on either side will capture that central 95%.
But let's be real. In the actual world, we almost never know the true population standard deviation, sigma.
Never. You'd have to have measured everyone.
So what do we do when we only have the sample standard deviation, which we call SECness?
That is the far more common scenario. And this is where the T distribution comes into play. When we don't know sigma, we have to estimate it using S. And that adds another layer of uncertainty. A statistical fog.
A fog, I like that.
To account for that fog, we use the T distribution, and it requires us to calculate something called degrees of freedom. It's just your sample size minus 1.
So n minus 1.
And when we use the T distribution, our interval will actually be a little bit wider than if we use Z.
So the T distribution is like a penalty. We're paying a small price in precision, a slightly wider net, because we had to guess the volatility from our sample.
That's a perfect way to put it. You're penalized.
Yeah.
The smaller your sample, the bigger the penalty. But as your sample size gets bigger, the t-distribution basically just morphs into the z-distribution anyway.
Let's apply this. The credit card debt example. We sampled 70 households, so n equals 70. We found the average debt was $9,312.
And the sample standard deviation S was $4,007. So since sigma is unknown,
We used the t-distribution with 69 degrees of freedom.
right, you run those numbers with the correct t-multiplier, and the calculation gives you a margin of error of $955.
Which means, and this is the payoff, we are 95% confident that the true average credit card debt for all U.S. households is somewhere between $8,357 and $10,267.
A much more informative statement than just saying 9,312.
Absolutely. But this is the perfect time to clarify what 95% confident really means, because it's a common trap.
Oh, it's the biggest one. It does not mean there's a 95% probability that the true number falls inside this specific interval we just calculated.
So if it's not about this specific range, what is it?
It's a statement about the process. It means that if we were to repeat this whole thing, take 70 new households, calculate a new average, draw a new interval, if we did that over and over and over,
100 times.
then 95 of those 100 intervals would successfully capture the true fixed population parameter. We trust the method, even if we can't be sure about this one specific net.
Okay, that's a crucial distinction. Now, before we move on, what about sample size for means? I mean, a rule of thumb.
Yeah, the general rule is that n greater than or equal to 30 is adequate. That's usually enough to invoke the central limit theorem and trust your methods. If you have fewer than 15.
You're on thin ice.
You're on thin ice unless you are absolutely certain the underlying population is already normal, which is rare.
Good to know. Okay, let's shift gears. We've been talking about continuous data like debt or height. What about simple categorical things? Yes, no, success, failure.
Proportions.
Right, estimating the population proportion, P.
The general form is exactly the same. Your sample proportion, P bar, plus or minus the margin of error. But for proportions, we always get to use the z-distribution.
Oh, that's simpler.
It is. But there's a condition. You have to meet the success-failure condition.
Which is what?
You just have to check that you have at least 5 successes in your sample and at least 5 failures. If you have that, you're good to go. The math works out.
Okay, so the Women Golfers Survey, they polled 900 women, and 396 said they were satisfied with tea time availability.
So that gives us a sample proportion P bar of 0.44, or 44%. We use our Z multiplier of 1.96.
And the resulting margin of error is 0.0324.
Right. So we can say with 95% confidence that the true satisfaction rate among all women golfers is between 40.76% and 47.24%.
Wow, that's a huge spread. That could be the difference between a real crisis on your hands and just, normal grumbling.
It's the difference between action and monitoring. That's why the interval is so important.
So we've covered how to calculate the interval once we have the data. But in the real world, the big decision happens before you even start. How many people do I need to survey to get the precision I want?
Exactly. You're solving for n, the sample size.
You set your desired margin of error, E, and your confidence level, and you work backwards to find N.
But this is where a practical dilemma comes up for proportions. The formula you need to calculate n requires a planning value for the proportion itself. We call it P star.
Right. So to calculate the sample size, I need to know the very proportion that I'm trying to find with the sample.
That's the chicken and egg problem. Of course, you don't know it yet.
So how do you get around that? What do you plug in for P star?
The sources outline a few ways. You could use a result from a previous study or an expert's best guess. But the most important method, if you have no information at all, is the conservative approach.
The conservative approach. I like the sound of that.
It's an act of statistical risk management. You choose a P star of 0.5, 50%.
Why 0.5?
Because the variance term in the formula, which is P star times 1 minus P star, that term is at its absolute maximum when P star is mono 5.
Ah. So you're planning for the worst case scenario, the most volatile possible outcome.
Exactly. You're calculating for the highest possible variance, which gives you the largest possible sample size. It guarantees you will meet or beat your precision goal no matter what the real proportion turns out to be.
It's like buying statistical insurance.
That's it, exactly. It's the cost of being certain about your precision.
So let's compare. If we wanted a tight margin of error of, say, 0.025.
Okay, 2.5%.
If we used the prior Gulf study result where p-star was 0.44, we'd need a sample of 1,515 golfers.
Right.
But if we were starting from scratch, using that conservative, play-it-safe approach with p-star equals 0.5.
Then you would need 1,537.
So only slightly higher, just 22 more surveys.
But those 22 extra surveys are your guarantee. It ensures that you hit your target no matter what.
We successfully cast our net today. We define the confidence interval as that crucial range of reasonable values.
Yep. We saw how the central limit theorem lets us use the z, or more often the t distribution.
And that t distribution is our penalty for having to guess at the data's volatility.
Right. And finally, we learned how to engineer our sample size for the precision we need, using that conservative value of 0.5 for proportions.
So for you, the learner, the core takeaways are pretty clear. First, always demand the interval, not just the single number.
Always.
Second, remember that the t distribution is that reality check we have to use to account for uncertainty. And third, when you're planning a survey, use that p-star equals 0.5 rule to guarantee you succeed.
And if I can leave you with one final thought, we've stressed what 95% confidence means. It's about the reliability of the process.
Right, not this one interval.
Remembering that distinction, that it's about the long-run probability that the method works, that's the true test of statistical literacy.
The process versus the product. That's what separates basic statistics from real insight. That's a wrap on this deep dive.